Welcome to the channel where all you gotta do is have that turbocharger talk. So this is a turbocharger that's been on my desk for 25 years, 30 years, probably more like 35 years. Anyway, a long time. This is one of the first Garrett GT40 turbochargers. And I had the privilege of working there early in my engineering career, so I asked my boss if I could steal some parts out of the junk bin and build me up a mock-up. So that's what I did. So this is a hodgepodge of parts I found laying in the garbage bin. Happens to have a billet compressor wheel with a boreless, which I think they never even came out with, or if they did, they went away. It's also has a weird turbine housing or compressor housing, which I'll go over a little bit, but there's a lot of information on the internet about what a good turbocharger is and how to size it for your car, and this may not come to a surprise to you that I disagree with a lot of what people are saying. A lot of it's correct, but they don't give you the full story. So in this video, I'm going to attempt to kind of explain what a turbocharger is, what makes it work, all the components of it, and then some design criteria around the components. And then that's not as interesting as a non-engineer. Most people out there probably want to figure out what is the best turbo for their application, and that's challenging to explain and come up with criteria on why, but I'm gonna attempt that. So there's, well, hundreds really, but dozens of choices that are kind of appropriate. A lot of people just look at the horsepower number and go, I need to have that, but that's really not the right way to do it. You have to understand what your pressure ratio is going to be, where your surge limit is, if it's on a compression ignition engine or a spark ignition engine, 2-valve, 4-valve. Like if you want to make 600 horsepower with a 4-cylinder, it's different than making 600 horsepower with a V8. So you have to, it's not the same turbo for those applications, right? And it's a challenging time right now with turbos because all the new technology is really, in the aftermarket turbo world, is coming from diesels, right? It's diesel technology that it's being carried over into the automotive aftermarket. And diesels, you know, it's lots of boost, right? You can't put too much boost into a diesel. So, you know, 30, 40, 50 PSI is very common for a diesel, like a standard production diesel pickup truck has 30 PSI. It just does. And even ones 20 years ago had 25 PSI. So, and that's unheard of in a car, but basically they're taking the technology, they're mixing and matching some pieces, changing the ORRs, changing, you know, little stuff, but essentially all the engineering and development that goes into modern turbochargers is based off of the diesel market, really. So I'm going to go over how this one works. This is a GT40, which is, you know, pretty old technology. This was, I think I worked there in 1992 when this GT series came out. It was originally called the NGT Turbo, which stood for Next Generation Turbocharger. And unfortunately, No Good Turbo was the acronym that people used, and that was inappropriate, so they just dropped the N and called it the GT, which sounds better, sure. But that's where the name came from. The only reason I know that is because, you know, I was embedded in the design team. Didn't really do any design work on this turbocharger, little bit. I was there as an engineer, but I mostly did test engineering stuff. I scheduled tests and made sure the hardware was available and got it assembled and balanced, and went to priority meetings and made sure that I was in the front of the line. And so it was pretty mundane work, but it was pretty cool. I was a senior in engineering school at the time, and I did a 6-month internship there. So it was pretty cool going to a place where everybody had a turbocharger on their desk. And so that's why I wanted a turbocharger on my desk as well, but one that I could, you know, store pencils and stuff in. So anyway, I'll get up a little bit closer here. You don't want to look at my ugly face anyway. And we'll go through what all the components of this are, what they do. There are iterations of them. There's variations for different applications. I'll go over that a little bit. And any questions that I don't answer, I probably have the answer somewhere tucked inside my brain. Just shoot message while you're pushing the subscribe button. Use your thumbs or your index fingers or whatever to type me a message, question, comment, whatever. Okay, so this is my display model. Again, this is a Garrett GT40. This is actually designed for a diesel. So it has a split housing, turbine housing. So essentially what that does is there's exhaust pulses from, this is for an inline 6-cylinder engine, but you could use it on, you know, really anything. And so they split the manifold, 3 cylinders on this side, 3 cylinders on this side, and you get some pulse energy. Like what makes this turbine spin is entropy, right? Pressure and temperature. But if you run this on a gas stand, which is basically just a combustor shooting compressed gases, exhaust gases from that combustor in here, and it's a steady flow, you'll get a turbine efficiency of, you know, 85%, 90%, something like that. But if you run it on an engine, when you measure the pressure, it's measuring the pressure, the bulk pressure. It's not measuring the pulsation pressure. And if you run this on an actual engine, using that as an input, you'll get like 105 or 103 or 100, you know, plus 100% efficiency usually, or very close to 100%. Because it's utilizing the pulse energy, and that's what this does. This split housing gives you an advantage in turbine efficiency by using the pulse energy. But maybe we'll get back to that. But I'm going to start from this end of the turbocharger and work that way. So again, this is the turbine housing. It's a divided housing again. There's also versions of these that are you know, integral wastegates. So they basically have a bypass that goes from here to here. So it just bypasses the turbine. People call them wastegates because you're wasting the heat in the exhaust. And that's a way to control how fast it goes. Because if this spins too fast, it, you know, flies apart, and that's bad. Or it makes too much boost, and then your engine flies apart. So there's wastegates housings available. So this is typically made out of like a cast iron. There are special alloys that everybody uses to make them high heat and easy to machine and easy to cast and stuff like that. So that's this part. Some applications use stainless steel, which is way more expensive, but they can make it thinner. And the reason they can make it thinner is if this thing flies apart, all these pieces inside that are spinning at this one I think spins about 140,000 RPM. So all these pieces have to stay inside. So if you don't make it out of thick enough material, those pieces fly out and chop people's legs off. It's bad. So if you use a stainless steel, it's a stronger material than this cast iron is, so you can use a thinner housing and it's lighter. Plus it doesn't get all rusty, ugly looking like this. The next piece in line is the turbine, right? Obviously that's this thing here. There's various shapes and sizes of these things, which I'll go over what all the jargon means a little later, but basically this captures the energy from the exhaust, which is primarily heat, but also pressure. So this doesn't have any oil in it and stuff, so, you know, it's just lubricated with WD-40 and dust right now, but so that's the turbine, and that's its primary job. It's typically made of Inconel, and then it's friction welded to a steel shaft. So this shaft is made out of steel. This turbine wheel itself is made out of Inconel. There is a little piston ring right here. I'm not sure if you can see it, but there's a piston ring right there, and the job of that piston ring is to keep the oil that's in here. It's not pressurized oil, it's just drain oil. from going into the turbine and following up the turbine, and catalytic converter clogged up, and oil consumption, all that stuff. So that's all that job is. Sometimes they have 2, sometimes they have 3, sometimes they have 1. So that's just a seal. It's piston ring. The outside is snap fit to the housing. So one of the failure mechanisms it has with these, if that gets too hot, it loses its preload and then it spins and then it doesn't work anymore. So as you can see, this one, the housing or the shaft is spinning, but the piston is not. So that's what it's supposed to do. This little piece in here is a heat shield. So as you can imagine, this thing gets really hot. 1,000, 1,500 degrees Fahrenheit. They'll definitely glow red in your car when you're pulling a trailer up a hill or whatever. So, and you don't want the oil to get hot. So there's this heat shield that's in there just to isolate the heat from the heat that gets to the center housing. Speaking of center housing, that's the next piece of the puzzle. So this is the center housing. There's a couple of versions of this. Some people actually make these out of aluminum. Most people make them out of cast iron because the bearing clearances are, this thing spins 140,000 RPM. Some smaller ones spin 280,000 RPM. But somewhere in the range of, big ones to little ones, it's usually between 70,000 and 220,000 RPM. You'd probably get 85% of the family of turbochargers used in passenger cars that stay within that sort of range. So this is the center housing. Some of them are just oil in, oil out. You can see this is the pressure feed. Feeds that bearing there, feeds that bearing there with some cross drillings. Some of them have water cooling as well. If you can't keep the heat from the turbine housing getting into the center housing, you can cool the center housing. So that's a little bit more expensive, more plumbing, more things to break. This one happens to be a version that doesn't have a water-cooled center section. So these little brass-colored pieces, those are bearings. So, and they're what are called full floating bearings. So you can see this guy here. One of them is kind of spinning. But when this thing is in a vehicle and it's not full of dust and WD-40, let's say this shaft is spinning 100,000 RPM, this bearing here will be spinning 50,000 RPM or so, plus minus 10,000, right? So it's a double bearing system. So the relative motion isn't between one shaft and a housing, it's between the bearing. So that does 2 things for you. One, it reduces the losses in the bearing because the shearing is happening half as much, but 2 times. And it also, if you've ever looked at an advertisement for a turbocharger, like a used one, they'll say, oh, it has minimal shaft play. Well, the shaft play is not a problem. That's intended to be there, right? I don't know if you can see that. There's quite a bit of movement here. And that's not because this is a cutaway. That's intentional. So basically what happens is there's a film of oil on the outside and a film of oil on the inside of this bearing. And that acts as a damper because this thing is going from 0 speed to 140,000 RPM. It's going through some critical modes. And if you don't damp those critical modes, they will run away from you and shit will fly apart. Elbado. So this is basically a damper and a bearing system. So that's why they spin. Some older turbochargers don't have this spacer in the middle here. This is I don't even know if they're still using this on the Garrett stuff, but this was a innovation that came with the GT series. But basically the older ones had little snap rings, were really finicky to get the little snap rings in place. Like they had a snap ring on each side of each bearing to hold everything so the bearing would stay in place, right? Because you have to have this bearing, this little feed hold of the bearing has to be lined up sort of with this oil feed in the channel. So that's what that job is. So those 2 bearings control the shaft radial play. In the axial direction, there's this thing right here, which is the thrust bearing. And there's little ramps on each side, and it's pressure fed, and there's 2 ramp, 3 ramp, 4 ramp, 5 ramp. There's some with full circle ramps, but basically when you put a pressure across the turbocharger, big pressure ratio, it pushes the shaft this way. So that load is depending on what pressure ratio you're running, you have to have a bigger thrust bearing. Unfortunately, the thrust bearing is the biggest drag of all these bearings, right? These ones have relatively low load, low losses, low torque losses compared to this thrust bearing. So that's another thing when you buy a turbocharger with a 3-to-1 pressure ratio, it's going to have a lot of loss in the thrust bearing. And if you buy one that has, 2-to-1 pressure ratio, which is like 15 psi, it'll have a smaller one, and so it'll spool up faster. So the next thing we have here, and this one's a carbon seal, but there's going to be a seal in between the compressor and the center section, because there's oil in the center section, and you don't want that leaking into the intake. So just like you don't want it leaking into the exhaust, you don't want it leaking into the intake. So this one happens to be a carbon seal, and a carbon seal is a much more positive seal. The other type of seal is a dynamic seal. I don't have one laying around handy, but I think I could probably find a picture and put it up there. Dynamic seal will have less drag loss, so it'll spool faster, but it won't seal as good. So if you have a carburetor on the inlet of the, some people do that, put a carburetor in there, run this wet. Not a great plan, some people do it. Or if you have a scenario where you're in a really dusty condition, your air cleaner gets dusty and dirty and filled up, and you have a lot of vacuum here, that'll cause your seal to leak, and you don't want to use a dynamic seal in that scenario. You want to use a carbon seal like this has. So this piece here is called the backing plate. It's basically just a disc, doesn't really do much. It's just a interface between mounting the center housing to the compressor. Then moving farther to the right, we have a compressor wheel. There's various versions of these compressor wheels, different backward curvature, different number of vanes, splitter vanes, not splitter vanes. This one happens to have splitter vanes. So that's these half height or 3/4 height vanes. That helps a lot of things, helps efficiency, it helps noise. But the other thing that it helps is if you put these splitter vanes in line with this little slot here. So this housing is called a ported housing. So this is kind of a unique compressor housing, and I don't think it ever went into production, but as you can see, it has a piece here and a piece here that just press fit together to make all these passages easier to manufacture. Again, I think I found this in the scrap bin, and I asked my boss what it was, and he went, "Oh yeah, that was a ill-fated attempt." And it worked. It's just the efficiency, this mismatch in here made the efficiency less good. So I don't think they ever went into production with it. The cost wasn't worth the less efficiency, but basically this little slot is a communication from the inlet to the splitter vane. And what that does is when you get into the surge area, which is like your turbine's spinning fast, your turbocharger's spinning fast, and then you let off the throttle, whether you want to slow down or shift gears or whatever, and your throttle blade closes. So now you have this thing spinning really fast, and basically it's like you put your hand over the outlet. It doesn't have any place for the air to go. And that gets into an unstable region, and some people think that's a cool noise. It's really hard on everything. It's hard on the thrust bearing, it's hard on the teeth, it's hard on all your downstream piping and stuff. Limits the life of your turbo. Try to stay out of it, even though it sounds cool. Yeah, don't do it. But that's what this is for. This makes it so you don't need a blow-off valve. So the circulation just kind of goes, around and round and round like that. So that's what that is. And then compressor housing. Obviously, this is, I think I already explained what it is, but basically it's, there's a little bit of confusion probably. You can see on here, it says A or R 22. So sometimes that'll be in millimeters, sometimes it'll be in inches. There's 25 times difference between the two, 25.4. So it's pretty obvious this is 22. So what that means is you have a compressor wheel, and then you have a housing that looks like that, right? And then your wheel's in here. So if you take a cross section through any place on this housing, the center of the area, let's say this area is round here, elliptical or whatever, the center of the area, that's your R, and this is your A. This is the area of all this stuff in here. So A over R is equal to 22 millimeters, right? So if this is 10 millimeters, that's going to be 220 square millimeters in area. And anywhere you do that, it's going to be constant, right? This is a constant A over R. Some other companies like Schweitzer and stuff don't use A over R, but I think probably all the modern turbochargers do. But basically what this does, it's more critical on the turbine side than it is on the compressor side, but basically what it does is the smallest area that you have is right here, right? That is the smallest area of the housing. So that area over that radius stays constant. You can see this one is a bigger radius and it's a bigger area. So that's how that works. And if you make a small A over R, it spools up faster. And if you make a big A over R, it's really lazy but has a lot of flow. So, and there's combinations of turbochargers. You can have the same wheel and change the compressor housing or the turbine housing and get very, very, very different performance on your vehicle by doing that. So, but anyway, that is the basics of all the pieces inside a turbocharger. Some more modern turbochargers have like a speed sensor in here, which is really nice because most turbocharger manufacturing companies will give you a map. Okay, so this is the compressor map for the G25 660, and this is the surge line right here. Yeah, my mousing skills are terrible, but basically all of this here you don't want to operate. So, and how you would operate there is like if you're 5,000 RPM and, well, more like 8,200 RPM in fourth gear. So you're up here somewhere and you left off the throttle, your flow is going to go to 0 or close to 0 pretty fast. So this is bad. This is why blow-off valves exist. And if this didn't have a ported housing, this would kind of look like that. And so this would all be less useful up here. So that's how the surge line is. There's things you can do to, make it better. Better turbochargers do that, but it's hard on everything. It's hard on all the piping. It's hard on the thrust bearing. It's hard on the compressor wheel. These are the speed lines. So this is 95,000 RPM, 115,000 RPM, so on and so forth. So, and then this is the pressure ratio here. So 2-to-1 pressure ratio, that's basically 2 atmospheres, about 15 psi-ish, depending on your altitude. And then 3 is 30 psi, 2 atmospheres above. This is all... this is the pressure ratio between the inlet and the outlet. So the inlet pressure, that's 1 atmosphere, right? So that's as low as you can get, unless you go, outer space or something. So 2-to-1 is double that. So atmospheric pressure is about 15 psi, 14.68 or whatever. So this is 14.68. Corrected airflow, this is pretty self-explanatory, but basically, as you can see, this one is rated for 60 pounds per minute, but that's like right here. You're down in the 60% range, right? 79, 78, 77, 76, 75, 74, 73, 72, 71. Oh, they start going in increments of 5, yeah. So it's really bad when you don't want to run over here. So really the limit where I would consider this an acceptable area to run is about in here somewhere, which is about 55 pounds per minute. Somewhere in there is about as far as you'd really want to go. You don't really want to go to 60. If you have to, it'll work.
They've tested it there, obviously. One more piece of information on this map, and actually the turbine map is important to understand how they came up with that. So basically, when they run a turbine map, they run the compressor map and the turbine map at the same time. And you'll see the turbine map kind of look like that. Different ARRs will look like that, like that. And what they do is they run on RPM. They run 65,000 RPM, constant speed. And then they change the pressure ratio to get like a little hoop like that. And then they run 95,000 RPM. And they get a little hoop that looks like that. And then they run, right? And they keep doing that. And they get a little hoop. And the reason they have to do it like that and not get a full turbine map is because they don't have like a turbine and a dynamometer to absorb how much power that thing's putting out. They're basically using the compressor as the dyno absorber. So they're using that as the load. So they only have so many opportunities. Like at that speed, they can only change the pressure ratio of the compressor by restricting the outlet or restricting the inlet or both to get this little hoop here, right? And then they take the peaks of the hoops and they just kind of make a flow line out of them, a trend line, as it were. So there's no guarantee you're going to be running at that point, though, right? This just happens to be the most efficient point of that turbine wheel at a characteristic point that the compressor wheel on the given test achieves. So kind of take this turbine housing or this turbine map as a grain of salt. Like, it's not like you could take the same turbocharger, same hot stage, turbine wheel and same turbine housing, put a different compressor wheel on it, and you will get a different map for the turbine. Because there's different load points at that speed and that load that make this little hoop curve different. So you kind of got to squint your eyes a little bit. And I mean, I'm sure somebody with the resources of Garrett could come up with a dyno that could absorb at 150,000 RPM. But it would be very expensive and time consuming when what they do is easy. They've been doing it for 50 years more. Is they use the compressor as the load. And you can kind of get an idea of what the turbine efficiency is. And of course, this is on a gas stand, so it's going to be different in the car anyway with pulse energy, yada, yada, yada. So just keep that into mind that don't put too much emphasis on the turbine map efficiency. And the other thing you have to understand about the turbine efficiency, this is a turbine map, and these are just 3 different A over R turbine housing. So this is the big housing. This is 0.92 A over R, and this is 0.72, and this is 0.49. So this one here is going to spool up real fast. But at the top end, your power is going to go to shit because it only flows 15 pounds per minute, whereas this one flows to almost 24. So not double, but close. And as I was saying earlier, the way they run this is they run a speed line, and they get a little curve like that at each speed line, and then they cross all the peaks. Same thing with this one and this one. So the other thing that you need to understand about a turbine map is if you look at how much mass flow goes through each one of these. The mass flow on the compressor side is 60, and the flow on the exhaust side is 25. But m dot in has to be the same as m dot out because it just does. And what you're not considering is the wastegate. The wastegate, some of that 55, it's even worse than that, right? Because let's say you have 60 pounds per minute going through the compressor, then you're adding fuel to it. So that's another, whatever your air-fuel ratio is, you're adding mass. It's not a huge amount, but it's something. And then half of it is going to get bypassed because there's no way you can get through the turbine. So anyway, keep that into consideration when you're, sizing this stuff. Understand that boost pressure does not put you on this map, right? Because you have a turbocharger, and then you have some pipes, and then you have an intercooler, and then you have a throttle body, and blah, 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 blah. All that stuff in between. The pressure here and the pressure here is different. So you have to compensate for that. Not only is the pressure here and the pressure here different, but if you have an intercooler, that intercooler has, not only does it have pressure losses, but it's also cooling the temperature of the fluid going through it. So that will shrink. The volume will go down. So the pressure will go down. Okay, so this is some calculations I've made. I use performance trends as a input. So I have cam timing, cylinder head flow, exhaust flow, throttle body flow, compression ratio, yada, yada, yada. All that stuff in there. Put the approximate turbo calculation, turbo parameters in there. And it gives me a curve. This is the normally aspirated curve, which is pretty close to what the stock dyno curve looks like for the stock motor. And then this is like 12.5 pounds of boost. So it makes just about 1,000 horsepower and 875 foot-pounds of torque. That's with two of these turbos. So ambient temperature, 75 degrees, reasonable. This is barometric pressure. Now, barometric pressure at low speed is different than it is going to be at high speed because you got air filter restrictions and intake piping and stuff like that. So I kind of made an estimate of that. This is the boost pressure. Not the boost pressure in the manifold, but the boost pressure at the turbo, which includes all the, losses in the system. So this is the actual pressure ratio, and going by this map, this is what my compressor efficiency is going to be. So you see the peak here is at 79%. You're not in it for very long, right? You go through it quickly at 4,500 RPM, and then it's all downhill from there. And then I have this to calculate the compressor. Well, this is the discharge pressure. So it uses all this information. That's the discharge from the compressor. And then from there, you look at the intercooler efficiency and the water side temperature, which people say that liquid air intercoolers are less good because you have two heat exchanger efficiencies multiplying together, and that's very true. But you also have less piping losses. Like you might lose, like a Super Coupe, for instance, has an air-to-air intercooler on it with an Eaton supercharger, and that has like 14 pounds of boost. And the piping is like 5 pounds of boost of that. That's putting that Eaton supercharger in a really terrible position. That extra 5 pounds of pressure loss going through all those intercooler piping and connections and back to under the intake manifold. And it's quite a disaster, actually, even though those cars do run okay. So that's why intercoolers that are liquid air are better, in my opinion, which is why the Allen one had that. But anyway, this one calculates the water side temperature goes up a little bit. I kind of guessed on that. And then this is data from my Flowbench extrapolated data because my flow bench doesn't flow 1000 CFM. So square the pressure ratios will give you the delta, and it goes up. Right? It might be 2 psi at low speed, but it's going to go up. And then with all these calculations, this is the outlet temperature. So this is what the temperature of the charge air is inside the plenum.
Okay, so that brings us to the topic at hand, the Fastang. So, as you may or may not know, Dad is getting a 5-liter BMW V10, the S85, which is pretty decent flowing heads, and it spins 8,200 RPM, makes 507 horsepower in the production car. This car is going to be 1,200 pounds lighter, so that'll help. And I've chosen this particular turbocharger for many reasons, but I'm going to go over a few of them right now. This is the latest in Garrett's line of turbochargers. This is the G series. So the way it is it was the NGT, which turned into a GT, and then there was a GTX, and then a G series. So this is the latest and greatest of Garrett's line. So it is a water-cooled center housing. It also has V-bands on the exhaust, which is really nice. Trying to get to these little bolts, especially in the car, is a giant pain in the ass. So V-bands, awesome addition. This one also has an internal wastegate, which is nice. See that little valve in there, flippity floppity. So that's nice. I have this taped up for a couple reasons. One, so it doesn't get dirt in it, but I did have to scan it to make sure it fit in the vehicle. So as you can see, this is also a ported housing. It has this little shroud here where it can recirculate, and there's little groovy in there. So this one doesn't have splitter vanes. But the reason I chose this is a G25. So 25 is the frame size. There's also 28s, 30s, 35s. Kind of similar to Garrett's methodology. This one here, this is on the Bronco project, but this is a GT42 dual ball bearing. And this one here is a G25 ball bearing. So internal wastegate. It also has a nice feature, the speed sensor in it, but you can just pop this off and buy a speed sensor and stick it in there, and it'll measure the, I don't know if you can see that little drilling in there, right down there. That's where the sensor measures counts the teeth as it goes by. And this is a G25-660, so this is good for 660 horsepower. Kinda. Okay, so this, after you do all these calculations, basically what you end up with is a compressor map with little dots on it. So these are the various plots on the dyno curve, or the simulation of the dyno curve. So this is like 3,000 RPM, 3,500 RPM, 4,000, blah, blah, blah. And as you can see, low speed, you're not making much power. You're pretty much making normally aspirated power, barely any boost. You're kind of in a shitty window, but you're not doing much work, right? The pressure ratio is low. It's only 3 pounds of boost, 5 pounds of boost. Up here you get up into the 12 pounds of boost range, and now you're starting to get into the efficiency island. And then pretty decent through here, right? You're at 78, 7,900. And this point here is probably like 6,500 RPM, something like that. And then when you get to 8,000 RPM, you're kind of falling off the edge of the world. So you're probably thinking, well, what were you thinking? Why didn't you pick a turbo that's better than that? And I'll go over that. But basically, this is 12 pounds of boost. You're dropping down into the 74% range up at the top end, which on a road course you
don't usually use that much, right? Your cars don't last that long if you're shifting at red line every corner. There's a lot of corners. So this is an alternative map. So basically you can control the wastegate valve and you can let your boost go up with RPM, right? So now, as you can see, we're running 17 pounds of boost instead of 12 pounds of boost. Now we're really, really in the efficiency island. The smallest number we're getting to is, 76%, 77%. So that's pretty decent if I'm going to go that route. And the only really other alternative I had was this one, this is a G30, which is a bigger frame size, so it has a bigger turbine wheel and a bigger compressor wheel. So as you can see, this here, it's looking better, right? This is still 45 pounds per minute, so this is 950 horsepower or something like that, close to 1,000 horsepower. You're right in the efficiency window, but your efficiency window doesn't start at 79; it starts at 76. So instead of at 74% efficiency, you're only at 75 now. It's not that big of a difference. And this is a bigger compressor and a bigger turbine wheel and a bigger frame size, so heavier turbo, harder to package. And then if you do go to higher boost, now you're up here, your peak is 76 instead of 79 or 78. So if you look at all the, response time, inertia, bigger wheels have more inertia, so they take longer to spool up. So I made that compromise, right? I'm not expecting to rev this thing to 8,200 RPM every shift. So that brings me back down to, kind of reality where somewhere in here is going to be my maximum RPM, which is 76%, which the G30 never even gets to, right? So I could see somebody arguing that this has more headroom and this is the right turbo to choose, but that's why this is an interesting world to live in. We all make different decisions based on the same information. Thanks for watching. If you like this content and want more, subscribe, like, and share.